Good morning, ladies and gentlemen. Today we are going to be looking at the idea of finding formulas for compounds. In this case, we're going to be dealing mostly with empirical formulas, but today in our conversation, we're going to have two different types of formulas that we're talking about, empirical and molecular. And we're going to see if we can figure that out. But we're going to be using the mole concept to be able to determine that. So just to let you know, that's where we're headed today. So what is an empirical formula? I'm moving my computer a little bit to get my trusty little pen. Okay, an empirical formula is the simplest whole number ratio of atoms. So the lowest whole number ratio that you can get is the empirical formula. It is calculated by dividing the subscripts in the actual formula or the molecular formula by the whole number. So if we're looking at a molecular formula and we're asked for an empirical formula, we'd look for a whole number that all of the numbers in the formula have in common. And that would be the number that we reduce it by to find the empirical formula. So if we have C5H10O5, we can see 5, 10, and 5. Well, obviously they all have 5 in common. So that is the molecular formula right there. So we're going to divide that by 5 because 5 is the common multiple between them. And that gives us C1H2O1. So the empirical formula for this would be CH2O. Because remember, we don't have to write the ones. If it's only one, we just simply say it. Okay, so you get the idea of the relationship between empirical formulas and molecular formulas. Now, this situation that we're talking about applies only to covalent bonds. Covalent bonds are the only ones that can have multiple ratios of atoms of the same kind. So what about ionic compounds? Ionic compounds are always empirical. They are always lowest whole number ratios. So when we talk about an ionic bond, it's always an empirical formula. Examples of this: NaCl, one Na and one Cl. You'll never see it any other way. MgCl2, you will never see magnesium chloride any other way as MgCl2 because magnesium has a 2+ charge, chlorine has a 1- charge. That's why they come together like that. Aluminum sulfate, again, 2 aluminums to 3 sulfate groups. That is because of the charges on aluminum and sulfate. And so we can see lowest whole number ratios are always going to occur. K2CO3, that's potassium carbonate. Potassium carbonate again is K2 and 1CO3 because of the charges on K, a +1, and the charge on CO3, a -2. So ionic compounds are always empirical. Covalent compounds could be empirical or molecular. So the way you figure that out is simply by looking at if there is a whole number ratio, a whole number that all numbers will go into. So let's look at a couple examples. So here are some molecular formulas. So we see acetylene, C2H2. Oh, they have 2 in common. I divide that and I get CH. Benzene, C6H6. Oh, hang on. Its empirical formula is the same as acetylene. It's still CH because the whole number ratio in benzene is 6, the whole number ratio in acetylene is 2, but they have the same empirical formula. Ammonia, you see ammonia's empirical formula and its molecular formula are exactly the same. Why? Because you can't divide 1 and 3 any further. Hydrazine, N2H4. Well, 2 and 4 have a number in common, 2. I divide all this by 2 and I get the empirical formula of NH2. Ribose. Ribose is one of those sugars. We just talked about ribose. Ribose is C5H10O5. And we know that that has a 5 in it. So we get CH2O. And you look at glucose, C6H12O6. Notice the oses. They have the same empirical formula too. Not 100% positive if that happens all the time, but it seems to be happening quite a bit. Okay, so you can have the same empirical formula for a covalent compound for multiple compounds because they can have different ratios. And we'll figure out a little bit later how to calculate that. Okay, so no big deal right now. We're talking about empirical formulas only. Only the discussion of a molecular formula at this moment based upon the fact that molecular formulas are related to empirical formulas by a whole number ratio. Okay, so let's look. What is the empirical formula for C4H8? Is it C2H4, CH2, or CH? If we look at 4 and 8, I think we can clearly see 4 and 8, well, that's got a 4 in it, so we divide both by 4 and we get 1 and 2. So clearly, that would be the correct answer. What is the empirical formula for C8H14? Well, is it C4H7, C6H12, or C8H14? So C implies that we can't divide it at all. B, I have no idea. So 8 and 14, they both have a 2 in common. Divide by 2 and we get 4 and 7. So there is the correct answer for the empirical formula. Okay, which is a possible molecular formula for CH2O? So we've seen that before. Is this one C4H4O4, C2H4O2, or C3H6O2? So which one is possible? Yeah, B is definitely possible. I multiplied by 2. 2 times 1 is 2. 2 times 2 is 4. 2 times 1 is 2. So that's definitely possible. Any others? Oh, what about C? If I multiply by 3, 3 times 1 is 3, 3 times 2 is 6, and 3 times 1. So B and C are both possible molecular formulas for the empirical formula of CH2O. Okay, and we saw two others earlier, the ribose and the glucose. Okay, let's check. A compound has an empirical formula of SN, 1S, 1N. If there are 4 atoms of N in one molecule, what is the molecular formula? So is it SN? Is it SN4? Or is it S4N4? Now, the explanation here is actually pretty simple. We see the empirical formula. The empirical formula is 1S, 1N. We're told in the problem that there have to be 4 N's. If there have to be 4 N's, I can't just add a 4 to the N and not look at the S, because they have to be in a 1-to-1 ratio, which means that C is the only answer that can happen, because they can't be in a 1-to-4 ratio. They have to be in 1-to-1, and there have to be 4 N's. So A is not possible because there aren't 4 N's. B is not possible because there's not a 1-to-1 ratio. So C is the only answer that's possible there. All right, how do we calculate empirical formula? So if we're given some information like percent composition or experimental data, what do we need to do to be able to calculate empirical formula? So this is where I'm going to give you a methodology. It's different than the methodology I gave you for the mole conversions, but it's a methodology nonetheless, and it actually involves mole conversions as well. So if the calculation is based upon percent composition, we are going to assume 100 grams. What that basically means is the percents become the number of grams of each of those compounds that we have in that formula. Okay? After we assume 100 grams, if we need to, we're going to determine the number of moles of each element in the compound. Okay? Then we're going to divide each value of moles by the smallest value. So you can see what we've done. We've gotten masses here. Okay? Then we've taken those masses and turned them into moles. Now we looked at all of the mole ratios and we found the smallest one. And so then we're going to divide all of those mole ratios by that smallest one. And one of them is always going to become 1. And then once we do that, if we have integers that are not whole numbers, then we have to obtain whole numbers if necessary. And we'll see a couple examples of that in just a minute so that you don't get too confused by it. So that is a step that may or may not happen. And then finally, we're going to write the empirical formula. Now, let me tell you, step 1 can be skipped if you have experimental evidence. If you have experimental evidence and you do not have percent compositions, you can skip step 1. So step 1 can be skipped if you have experimental evidence, but if you have percent composition, step 1 comes into play. Step 4 can be skipped if we have all whole numbers. If everything is a whole number, we don't need to multiply by an integer. Okay, so step 1 and step 4 are steps that could be skipped if the conditions are right. Okay, but all of the other steps are absolutely necessary to calculate. So let's look and see what we can do. We're going to start out with the percent composition. Adipic acid contains 49.32% carbon, 43.84% oxygen, and 6.85% hydrogen by mass. What is the empirical formula of adipic acid? So that's where we're starting. So we definitely have to start with the 100-gram assumption. We have to start with the 100-gram assumption. So the first thing that we need to do is we need to treat the mass, or percents as mass, and convert to grams. So we get 49.32 grams of carbon, 43.84 grams of oxygen, and 6.85 grams of hydrogen. That was pretty easy, right? All I did was take the numbers from the percent and change the unit to grams. All right, the next step is to convert to moles. So this was step 1. Now we need to do step 2 where we're converting grams to moles. So here we go, grams to moles. 49.32 grams of carbon to moles of carbon, we see 4.0107. Oxygen, okay, and hydrogen. Now I'm going through this quickly because this should be something that you know. Converting to moles from grams is something that you should be quite familiar with, and in all honesty, you don't have to add anything up here because you're looking at elements, and so you're just simply seeking the mass from the periodic table for each of your elements and changing it to moles. Now we need to start thinking about step number 3. Step number 3 says I'm going to divide by the smallest number of moles. So which number of moles do you think that we're going to divide by? 4.107, 2.74, or 6.78? Yeah, the 2.74 is the one that we're going to choose to divide by. So on the next slide, I think that we do that. 4.107 divided by 2.74 gives me 1.5. 6.78 divided by 2.74 gives me 2.47. We're going to just round that up. That's really close to 0.5, so we're going to probably round that up to 2.5 for the sake of ease. And then 2.74 divided by 2.74 gives me 1. So you can see that one of them is always going to be a 1. So these are the ratios to each other of these atoms in this compound. The problem is we do not have whole number ratios here. So let me show you the next slide so that we can see what we might have to do here. So when the number of moles for an element is a decimal, all the moles have to be multiplied by an integer to get a whole number. So you can see over here, if the decimal ending is 0.2, we're going to multiply by 5 to get a 6. If the decimal number is 0.25, we're going to multiply by 4. That'll round us up to the nearest whole number. If it's 0.33, we're going to multiply by 3. If it's 0.5, we're going to multiply by 2. And if it's 0.67, we're going to multiply by 3 again. Okay? So these are the ways that we do that. So which one are we going to choose for ours? We had 1.5 and 2.5. Yeah, we're going to do this one right here. We're going to do 2. So let's see how that works. Here we go. I multiply 1.5 by 2 and I get 3 as the ratio. I multiply 2.5 by 2 and I get 5 is the ratio, and I multiply 1 by 2 and get 2 as the ratio. Now you're going to say, Ms. Stover, I didn't have to multiply 1 by anything. It wasn't a decimal. But whatever you do to one, you have to do to all. You cannot do them to just one of them. You have to do them to all of them. So what is the empirical formula? Well, we have 3 carbons, 5 hydrogens, and 2 oxygens. So the empirical formula would be C3H5O2. Okay, let's try another problem and see if we can figure out the system here. Okay, so this one is from experimental data. So we have a 1.25 gram piece of copper and it's reacted with hydrochloric acid. After drying, the resulting compound has a mass of 2.64 grams. What is the empirical formula of the compound? So first of all, we have to know something here. This copper is going to bubble. Now, copper doesn't bubble vigorously in hydrochloric acid. It takes a long time for this to happen. But it does bubble, which means it's giving off a gas. What gas could it give off? Well, it's not a green gas. It's a colorless gas, so that means it's got to be hydrogen. So copper is reacting with chlorine in this particular case to form copper chloride. We don't know what it is. So we're not sure if it's copper 1 or copper 2 at this point. We're not 100% sure what's happening here, so we're gonna try to find out. So the first thing that we need to do is find the masses. Well, we see what the copper is. The copper is 1.25 grams. So the copper is definitely 1.25 grams. Then if we want to know how much chlorine is in there, and by the way, we are going to be getting to chemical reactions. So this is a chemical reaction that is going to become very familiar to you over time. So don't panic, okay? Do not panic that you're not completely understanding why it's chlorine and why it's not hydrogen. Just trust me when I say it's chlorine, and this is going to be appropriate for the lab that we're going to be doing, okay? So here we go. We have 1.39 grams of chlorine. So 1.25 grams of copper give you that many moles of copper. 1.39 grams of chlorine give you that many moles of chlorine. You can see which one's smallest. The copper is the smallest. I'm going fast, I'm sorry. Okay, so copper is divided by 1.0197. That gives us 1. Chlorine is divided by that too, and it gives us 2, so the empirical formula becomes CuCl2. I'm going to actually put